All right, guys, this is the Aerosol and Humidity Lab. We're getting ready to show you a few humidifiers and show you some aerosol, right? The last lab we saw high flow devices which utilize aerosol technology, right? The aerosol face mask, aerosol T-piece, aerosol tray collar, all of those things use the aerosol, which are the large volume nebulizers, right? They use the large volume nebulizer with one large bore tubing, then our drainage bag, and then another large bore tubing, right? And then whatever you put at the end is what we call the device. Also, remember that it uses the Venturi principle, right? Where I can open up the vanes and windows to see what FiO2 that I'm giving the patient. So this is aerosol, right? Aerosol you can see, humidity you cannot see. As I said before, a lot of times these lessons will run into each other, right? Aerosol humidity runs right into high flow, low flow, okay? It's because it's all one big pot, right, of respiratory. Now, today I'm going to focus on showing you the humidifiers, and then show you, just touch on the aerosol or nebulizers, right? These high flow device is an aerosol setup, but it's called a nebulizer, right? This is a large volume nebulizer. Large volume nebulizer because it has a lot of solution or a lot of distilled water. It's a large volume nebulizer because a nebulizer will make large water particles smaller, okay? They use a baffle, which is a little small device inside of your nebulizers that convert the water particles into a mist that you can see. That's what the baffle is for, okay? The baffle. This is a large volume nebulizer, and the breathing treatment is a small volume nebulizer, right? So this is a LVN for large volume nebulizer, is what we use for the aerosol setups. For aerosol setups, we use large volume nebulizers, okay? And then for medication delivery, we use small volume nebulizers, right? Small volume nebulizers, or SVNs, okay? Now, this is considered your small volume nebulizer. This is your SVN, which we will deal with a lot more when we get into the next lesson of pharmacology. Pharmacology, you're almost done. All right, so the small volume nebulizer is a small volume, right? It uses up to 6 cc's of medicine, right? Either medicine or hypertonic saline, hypotonic saline, normal saline, which you'll learn when we get into our pharmacology. The saline products are just for mucolytics. They move mucus, right? But also when we get into our bronchodilators and our oral corticosteroids or inhaled steroids, right? We can even do inhaled antibiotics like gentamicin and tobramycin. You'll learn those later. But we put them in here, right? We use a small ampule and we take off the top, pour it in here. This green device here is your baffle. This is the baffle. This does all the magic in a small volume nebulizer. What it does is it converts big particles into what? Small particles, and you can see them. That's always in there. If this is not in here, then your medicine would not nebulize, right? It has to have a baffle, okay? So this would be the small volume nebulizer, which is the medicine cup. Then we have the Briggs adapter, remember that? The T-piece, also known as Briggs adapter. We will put the mouthpiece on one end and a reservoir tubing on the other end, right? And then of course you have your small bore tubing that goes on the bottom, right? And then the rest goes to the actual flow meter or the nebulizer that you're using, okay? So this is a small volume nebulizer that produces a aerosol, okay? Aerosol, not for humidity, aerosol. All right, so let's look at some more. We talked about in the lesson, and sometimes you will have to zoom in on the video to see certain things, but everything on here now you should be able to see. Okay. Now we talked about humidifiers as far as aerosol and humidity is concerned. Okay. We said that humidity is absolutely necessary, right? So especially if my patient's nose or upper airway has been bypassed, right? Either from trauma or some kind of surgery that they have to have an either endotracheal tube in place, or if they have a tracheostomy, okay? So I'm going to show you up close what you're bypassing, okay? This is a cross section of an adult upper airway. All right, you see here's the mouth, and here's the tongue, and this is the nair, right? So this area here would be your nasal conchi, right? This is where the air comes in, or the gas would rotate around these tubercles, conchi tubernates, right? And they would moisten and humidify. Moisten and humidify the gas, right? And then it will travel to the nasal pharynx, oral pharynx, and then down into the airway, okay? Now, if this is bypassed, this patient is no longer using his upper airway. He has what's called a tracheostomy in place, right? The tracheostomy. You notice it's a cylinder, tubular-like device that is inserted into the trachea, okay? So this is in his trachea. Now, he will have to get all of his oxygen, humidity, and heat from here because he's not breathing through here, okay? So if I am a respiratory therapist and I have a patient with an artificial airway or his upper airway has been bypassed, I must heat and I must humidify that gas, okay? If not, I'm going to dry everything out from this point on. Trachea, bronchus, bronchi, bronchioles, terminal bronchioles, respiratory bronchioles, right? Everything is going to become dry, right? The patient's lungs will become dehydrated, and in your lesson, we learned the domino effect, right? We learned the domino effect of inadequate humidity. With that being said, sometimes patients still need humidity even if they have not bypassed their airway, right? We learned about croup, right? Croup is sometimes when the airway is swollen in children. That can cause croup or epiglottitis when the epiglottis is swollen, right? Somebody who has just been extubated. That means their ET tube has just been removed, right? Well, it's been in the throat for so long, or the trachea for so long, that it becomes irritated. So when we pull it out, it can swell, right? And so that cool mist aerosol through an aerosol face mask or face tint will allow that area to the swelling to go down, right? The edema to go away, the swelling go down. Sometimes we may even have to add medicine called racemic epi. If the swelling is so bad and we start to audibly hear stridor, right? Remember, stridor is the sound that you can hear away from the patient, right? It's like, because the vocal cords and the throat have all swollen, and we have to, cool mist may not work for that patient, so we have to give them some racemic epi, which is an alpha agonist, right, which will decrease the swelling by vasoconstriction, okay? Again, those medicine and those medicine terms will come into pharmacology on the next lesson. But you guys know I like to give you a taste of each one beforehand so that when we enter into that, it won't be foreign knowledge, all right? All right, now, some of the humidifiers. The first humidifier I already hooked up is the bubble humidifier. Remember we talked about the bubble humidifier will moisten the dry gas in the nose, right, through a nasal cannula. 99.9% of the time, you only use a bubble humidifier for the nasal cannula, all right? So what happens is, and you'll have to zoom in, when I turn on the leader flow, there's bubbles that the gas will come to the bottom of the bubble humidifier, right? And it will come up through the water and out of the nasal cannula, right? This will moisten the dry gas that's delivered to the nares, because medical gas is very, very dry, right? So after about 3 liters or 4 liters, you want to make sure that your patient is on a bubble humidifier so that they don't bleed, become really, really dry up in the nares and very, very uncomfortable, right? So the concept, or what happens for the humidification, is contact time, right, and particle size, right? So we want a longer contact time. So the longer that the water or the bubbles are interacting with the water, so the bigger the receptacle, right, the bigger the reservoir, the more humidity you will have, right? So this is a larger bubble humidifier, right? It's kind of large. The most ones you'll see look like this. See how much smaller this one is? Right? This is smaller than the larger one, right? And so what happens is this one has less contact time, right? So if I use this humidifier, then you'll notice that the gas that travels through here doesn't have much space to pick up a lot of moisture, right? So the contact time is less. So patients that are on this humidifier may have less humidity than those who are on that humidifier, right? Because of what? Contact time, right? Same thing we just learned about the nares, right? That is why the gas is in the conchi turbinates, right? It swirls around, not just straight in and down, it swirls around in a maze of conchi, right? Because we want to increase the contact time with the skin, right? The skin is moist, the skin is warm, right? And so the gas that's coming in will be able to have more time to contact that skin surface and increase the humidity and temperature, right? So this larger bubble humidifier will give us more humidity than the smaller bubble humidifier, okay? But they both work fine, okay? They both work fine. Now, we talked about relative humidity. And remember I said that humidity is either absolute and potential, right? If you have what you got, so write that down. Absolute is what you got, right? It's the amount of moisture that's in a gas at any given time, right? That's the absolute, right? And then you have potential, is what you can hold, right? You have the potential to do this, but this is actually what you have, right? Those two together, when we do the math, equals relative humidity. Relative humidity. And so I want to teach you a concept about it so that you can make sure you understand relative humidity. Now, if a patient has the ability, to hold, I'm going to do this. You can rewind and see that, but I'm going to write a few things here. If the patient has the ability, so let's say potential, POT, right, has the potential to hold 100 milligrams, right, and their absolute is what they actually have is only 50 milligrams, then their relative humidity is 50%, because they're only holding half of what they have the ability to hold, right? So if somebody tells you you have the ability to be a millionaire, right? You have the ability to be a millionaire. But if I ask you how much money is in your pocket right now and you say $100, then that's what you have, right? That's what you have. So you have not met your potential yet, right? You have not met your potential. So we talked about, let's look at a couple, and then we'll go into that concept about temperature and how the relative humidity is changed or stays the same. Okay? Now, say you have the potential to hold 44 milligrams per liter of water, right? And then let's just say at 37 degrees Celsius. At 37 degrees Celsius, you have the potential to hold 44 milligrams of water. But when I check you, you only have an absolute of 22 milligrams per liter of water, right? So if we put that into the formula, we say absolute over potential times 100, all right? Well, the absolute is 22, so that's 22 divided by your potential of 44, right? 22 divided by 44 is what? Let's look at it on here to make sure. I'll give you a chance to figure it out. 22 divided by 44 is 0.5, right? That is 0.5. Well, then we have to multiply by 100, and that gives us 50%, right? A relative humidity of 50%. Again, you'll have to zoom in as you're watching this video. Okay? So, absolute over potential. Absolute was 22, so it's 22 over potential of 44 divided, that's 0.5, and then you multiply that by 100, and it gives you 50%. So that relative humidity in this case is 50%. All right? Now, the concept you learned about whether the temperature will change the relative humidity or not. Well, in your notes, it said if you have a device, right? If you have a device like a cascade, and it's putting out 30 degrees, at 30 degrees Celsius, it's putting out 100% relative humidity, right? So they're saying at 30 degrees Celsius, the device that you're using, the humidifier that you're using, says that they can put out 100% relative humidity, right? Puts out 100% relative humidity, right? They said, but if the temperature increases, then the relative humidity will decrease. This is why. At 30 degrees Celsius, let's just use the numbers of 44 and, let's just say 44 and 22, right? At 37 degrees Celsius, let's just say you have the potential to hold 44, and you're holding absolute 44, right? So that is a relative humidity of 100%, right? That's 100%. At 30 degrees Celsius, you have the potential to hold 44, and you're holding 44, so that means your relative humidity is 100%. But what they're saying is, if the temperature increases, the temperature just went up, right, to 37. So an increase of temperature to 37 degrees Celsius, now what we have a potential to hold, let's just say you have the potential to hold 50 milligrams, right? But you're only holding those 25, right? You're only holding 25, right? So the temperature went up, so the potential went up, but the absolute still stayed the same, right? Not 25, I'm sorry, 22. 22, all right? So when the temperature went up to 37 degrees, the potential went up, right? The potential that it could hold was 50 now, right? But you're only holding 22. So that makes the relative humidity go down. So let's do the math. Let's do the math. 22 divided by 50. So 22 divided by 50 equals 0.44 times 100. Now the relative humidity is 44%. right? So the relative humidity went down. Relative humidity went down because the temperature went up, okay? The temperature went up, so the potential of the gas went up, but the absolute stayed the same. So that brought the relative humidity overall down, okay? Now, the opposite way. If the temperature goes down, then the absolute goes down and the potential goes down. So that can still give you 100% relative humidity, right? So let's look at it. If I have, let me get rid of some of this. If I have at 37 degrees Celsius, I have a potential of, let's just say, 50 milligrams of water, right? And I have an absolute of 50 milligrams of water as well, right? So that gives me a relative humidity of 100%. Okay? You got that? Now, if the temperature changes, if the temperature goes down to 30 degrees Celsius, then what they're saying is you can have a potential humidity of, the potential has gone down. So the potential went down to 25 milligrams, and your absolute also went down to 25 milligrams, right? Well, we still have 25 over 25, right? So that's still a relative humidity of 100%. Okay? So that's what they're saying. If the temperature goes down, relative humidity will stay the same, but the parts go down. Absolute goes down and potential goes down, but they're still equal. So that's 100%, right? That's still 100% relative humidity. If the temperature goes up, the potential goes up, but the absolute does not necessarily go up. So the relative humidity overall will go down, okay? It's just math, okay? It's just the math. Now, so let's look at a couple of these and wrap up the lab. This is the bubble humidifier for low flow systems like a nasal cannula, right? This is the low flow device, okay? Low flow humidifier. All right, now let's go into some more humidity and heat, right? This device here is an actual heater, right? This is a little heater that's kind of old school, but they use them in some places, right? Remember I told you that you must heat and humidify the gas, right? Now, you'll notice when you get to clinicals that some hospitals do not put heat on their aerosol devices for germ reasons, right? Breeding infection and germs. But so they just don't do it. Some hospitals do it. I know that Regional 1 chooses not to because they want to keep down the infection rate, right? They don't want to breed infection and germs with heat, right? But NBRC wants you to heat and humidify the gas, all right? So this is a device that simply would fit over one of your aerosol devices, right? This will slide in here like this. See that? This will plug up to the actual power, and this gets hot. This makes the water inside of here moist and hot, right? Now, as the gas comes out, it's heated and humidified, okay? So this is a type of heater for humidity, okay? Now, humidifiers. This humidifier here is called a Passover humidifier. This is the Passover. Because what happens is, as the gas travels from the source, which is, in Passovers are for high flow devices, right? So probably like a ventilator or some type of high flow nasal or something like that. It's a high flow system. So Cascade humidifier is for high flow system. You have large bore tubing. So you'd have one tubing coming from the machine, and then another tubing going to the actual patient. This one's going to the patient. Well, there's water in here, right? There will be water in here. And simply what happens is, as the gas travels through across the water, it picks up the moisture that from the water that's in here and takes it to the patient. You can't see it because humidity you cannot see. It's just water vapor, right? Water vapor. This is the passover because oxygen or gas passes over the water source. Simple, right? Now, what happens is it's just like being on Riverside in Memphis, right? If I'm on the Mississippi River and I'm standing on the banks and a nice breeze comes across the water, well, not only do I feel the coolness, but I feel the moisture from the water because that's the gas that's passing over the water and coming to me, right? That's the concept of the Passover humidifier. All right, Passover humidifier. This one is called a cascade humidifier. Notice the cascade is simply a Passover humidifier with heat, right? The cascade has what's called a tower. This is called a tower. This is the tower. You'll notice that on the tower you have a dial, right? That tells you how much heat you want to put on it, right? How hot it is. And this is the power source here. The plug will come off of here, plug up, and these down in here will heat up. These little tubes will heat up and heat the water, make it hot, right? And then as it passes over, it's hot. With this one, not so much. It doesn't have a tower, okay? So the Passover humidifier is a cascade humidifier without a tower. The Passover humidifier is a cascade humidifier without the tower, okay? Don't forget that. That's all it is. All right, so this is the cascade and this is the Passover. All right, this is another example of a cascade. This will be one that sits on top of a heater on your ventilator. Okay, it kind of just sits on top of a heater source. Okay, you'd have a heater source. This will slide in it and lock in place, and this metal part here will get hot. The water gets hot, right? And you have your large bore tubing from the machine to the patient. Same thing. But you'll notice it has this little feeder apparatus, right? This little feeder apparatus, right? And all it does is poke down into your water bag, okay? So I would put this in to the water bag, right? Lift it up, and you'll notice water going into here. See that? This is what the water comes from. This is a feed apparatus. This is normal saline for inhalation. See that? Inhalation only. This is not IV saline. This is simply distilled water for inhalation. And it's called a feed apparatus, right? And this keeps water inside of this cascade humidifier, all right? Now, what is this humidifier called if I have the heat off? If I have the heat off and there is no heat, it turns from a cascade into a what? Passover, correct. A simple Passover. But now that I have heat on it, it's now a cascade with a feed apparatus. Very important as a therapist, look at your water bag. When you come on the shift and there's a therapist leaving, make sure the water bag is not bone dry. If this water bag is completely collapsed and dry, you make them change it because you are responsible. If I'm your manager and I come in at 9 and I see this patient's bag is completely dry, I may reprimand you. But you may tell me, well, Mr. McCarthy, it was like that when I got here, right? That's even worse because you know how important humidity is and you knew it and you left it, right? So that's even worse. So make sure you have accountability, guys. It's very important. We know what the dangers of not having humidification does, and if we simply don't, if we overlook that, that could be detrimental to your patient from sheer laziness, right? Don't let the small things cause big problems. right? You worry, and I understand a lot of stuff is going on. People are having CPR coding, ventilators are going off, and you worry about a little water bottle. But we know those small things, if you pay attention to detail, they keep large things from happening, right? A lot of times if you don't humidify, you can, the domino effect all the way down to swelling of dry secretions later or pneumonia. And so if we do that, that's a large problem. So small things are very important, okay? So that is the cascade and the Passover, right? You also have the wick type Passover, right? The wick type humidifier. You have the with or without the wick. You're going to learn in your book. You need to look in your book or your lab book about the wick type, right? The wick type has, it's kind of like the Passover, but it has wicks down in it. That's like a material like cloth, right? And it soaks up the water that's in here, and that's how you get your humidity, right? It's called the wick type, all right? So make sure you read up on that one. Now, I spoke about the blender the other day. I just wanted to show you what a blender is. If I have an oxygen source and I want to control the FiO2, I can just simply hook this up to O2 and to air, right? See how this one looks? This is always the air system, right? And this is the oxygen system. I would hook up, I'm sorry, this is the DIS over here. This will be the oxygen side. See, it tells you hook up your auxiliary oxygen here, and then you'll have your air, right? This is your air here. And then, of course, this is where you will hook up your device. And then I can just turn this to what FiO2 I want, see? Now I don't have to worry about an analyzer, right? I can just use this, and this should give me the FiO2 that I want. Now, always use the analyzer to check it once a shift. You want to make sure once a shift that you are making sure that this is right. Because what if this says 100% and they only getting 30%, right? It may be broken. So you want to always keep that analyzer back up to make sure that you are giving the oxygen that you need, because FiO2 is very important. Very important. It can be good and can be what? Dangerous. All right? Now, so that's the Cascade. This is the Passover humidifier. Now, this is what's called the HME. This is the heat moisture exchanger. And they look different shapes and sizes. But the heat moisture exchanger is one of the most fascinating humidifiers you'll find. This is the heat moisture exchanger, right? What happens is it has a sponge and a filter. And when you exhale into it, when a patient exhales into it, right? They exhale into it, then it traps your heat and your moisture in this sponge. So you blow out of it or you exhale into it, and this sponge will trap the heat and moisture that you just exhaled. And then when you inhale, it gives it back to you. So when you breathe back in, you can feel the heat and feel the moisture of what you just exhaled into the device. This is an HME, heat moisture exchanger. Remember, we talked about this during our abbreviations and our medical terminology lab. All right, but this is it. This is an HME. Also looks like this, see? They have different ones. You exhale through it, and then when you inhale back, it gives you your heat and your moisture right back to you, right? Heat moisture exchanger, right? Heat moisture exchanger, also known as the artificial nose, right? Artificial nose. All right. The last thing that I want to show you is the ultrasonic nebulizer. The ultrasonic nebulizer is an older device that is used for sputum induction. If I want to get some sputum from you, then I need to get a machine or a device that can really get a lot of moisture into your lungs. Well, they some time back invented the ultrasonic nebulizer. This is the ultrasonic nebulizer, right? The water goes in here, and then this works off a magic principle called the piezoelectric crystal. This here, in here, the piezoelectric disc or piezoelectric crystal inside of there. And that converts large particles into smaller ones, but way better than a regular baffle, okay? Way better than a regular baffle. So much so that the frequency at which it produces particles is governed by the FCC. It's so good at converting large particles into smaller ones that the frequency at which it does it is regulated by the government, right? The Federal Commission, I forget, it's FCC. I have to look up and see exactly what that means. I forgot. It's not on the tip of my tongue. But the FCC mandates the amount of frequency that is delivered in this piezoelectric crystal, right? This piezoelectric disc turns water particles into smaller ones, right? And it does so well that the government has to regulate it, all right? So we have it here as your on and off switch, of course. And then also here is what's called the output, right? This here is your output. I can make it less particles or I can make it a whole lot of particles, right? Now, the amount and the frequency are two different things. The frequency is how fast it turns large particles into smaller ones, right? And the amount is how much do I push out after it's been converted, right? And so you'll look into your book, it does some boasting. The Ultrasonic Nebulizer boasts that 90% of their particles will be 0.5 to 3 microns, right? 90%. They say if you buy my nebulizer, I can guarantee that 90% of the particles that are coming out of this nebulizer will be between 0.5 and 3 microns, right? As we get into the lesson, you're going to learn about microns. That's the particle size. Remember, we said we don't want the particles to be too big. We don't want them to be too small. If the particles are less than 0.5 microns, then we'll inhale them and blow them right back out. They will never what? Deposit, right? We talked about penetration and deposition. And if they are less than 0.5, then they'll never deposit. They'll go in, be suspended, and come right back out, okay? If they're greater than 5, right, then they'll deposit in the mouth, right? Or like 3, 4, and 5, they will start to deposit earlier in the respiratory tract and not in the alveoli. That's what we wanted. So what did we say was the key factor in penetration and deposition? There's a few things, but the main one is the way you breathe. The number one way to ensure penetration and deposition are the slow, deep breath with an inspiratory hold, right? When in doubt, that's your answer. Slow, deep breath with an inspiratory hold. Slow, deep breath, hold for about 3 to 5 seconds, and let it out. That will ensure the best deposition and penetration. Now, you're going to learn in the lecture what the best particle size is. The best particle size for inhalation of the particles of the water or the medicine that we take is 3 to 5 microns. No, I'm sorry. 1 to 3. 1 to 3 microns. Right? That is the ideal particle size. You want the particles in your nebulizer or your medicine nebulizer to be 1 to 3 microns. That will ensure deposition of the drug or the particle in the alveoli. If they're greater than 3, they may deposit early, right? If they're less than 0.5, then they will come in and come right back out. So, ultrasonic nebulizers say 90% of our particles will be between 0.5 and 3, right? So that's good. I mean, 0.5 is a little small, but that's the majority of the particles that are coming out of this machine are falling in therapeutic range, okay? So this is the therapeutic range. right? Therapeutic range, excuse my chicken scratch, I forgot you're on camera. But therapeutic range is 1 to 3 microns. That's going to be in your lecture, it's going to be in your notes, okay? So that's the therapeutic range. That's what we want, 1 to 3 microns. Ultrasonic Nebulizer says that 90% of their microns will be between 0.5 to 3 microns. Ultrasonic Nebulizer boasts that 90% of their particles will be between 0.5 and 3 microns. Not only that, but it can put out 6 cc's per minute. 6 cc's of water per minute. 6 cc's of water per minute. That's the output, right? I can turn it all the way up and it will deliver 6 cc's of that 0.5 to 3 microns per minute. Understand that? Now, you think 6 cc's is not a lot, but if you look at a syringe and look at 6 cc's, that's a lot of water. If I squirt that completely into your lungs, you're going to have a bad day, okay? But since it's aerosolized, it doesn't hurt you as much, right? So that's why we use it for sputum induction. We can use a hypertonic saline, which you'll learn in pharmacology, and put it in a ultrasonic nebulizer, and we can guarantee we can make you cough. We can make you produce some sputum, right? And that's when I use that to go and get a sample of it from you, and then take it to get it gram stained, right? See if you have Pseudomonas, tuberculosis, whatever the case may be, or the suspicion may be, okay? But that's the ultrasonic nebulizer. You see, I talked about it a lot. It will be on the test, right? It will be on the test. 90% of its particles are 0.5 to 3 microns, and it can produce up to 6 cc's per minute of that mist, right? All right, that's the ultrasonic. And what is the magical part of it? The piezoelectric disc, or the piezoelectric crystal. Piezoelectric crystal. All right. That, in a nutshell, is aerosol and humidity, guys. We've already done the high flow device. I showed you the large volume nebulizer. I showed you the small volume nebulizer, right? They produce aerosol, right? And then the humidifiers, which is Passover, Cascade, right? The Cascade with the feed apparatus, right? I showed you the HME, heat moisture exchanger. And then I showed you the ultrasonic nebulizer, right? All of these are on the test. All of these concepts you will need to know as a respiratory therapist. Very important. Aerosol you can see, humidity you cannot see. Aerosol you can see, humidity you cannot see. Humidity is just a vapor, right? Make sure you study your indications of why we give humidity or why we would give aerosol, right? Know the difference between the two. Even though they mesh together, there are some differences between the two. And there are going to be some contraindications, right? Some contraindications of too much fluid, right? This ultrasonic nebulizer can give you 6 cc's per minute. But what I want to put this on a CHF patient, somebody who has pulmonary edema, right? I have to be careful. Somebody whose intake and output is positive 2,000-3,000 cc's, right? I have to think about that. I might want to hold off on some of these and use something different, okay? Because then I might add to their fluid intake and cause them to be drowning, okay? So it's very important as a therapist that you know your patient. Assessment, assessment, assessment. Know what kind of patient you're dealing with. Know their history and make the proper decisions. This is the Humidity and Aerosol Lab. There are going to be some other devices in your book that we don't have at the lab, but you can look at those, study those as well, okay? And I will see you for the live lecture.